Good afternoon, everyone. Uh, Welcome to the lecture 6 of the course on data structure and algorithm. So, in the previous lecture, we discussed about space complexity with a very simple example, uh, computation of summation of n number of real numbers. And we have seen that to compute sum of n number of elements, we may have two approaches. One is an iterative method using the for loop, and other is the recursive approach. And after analyzing both the algorithms, we have come up to the conclusion that the iterative method to compute the sum of n number of elements is better in terms of space complexity than the recursive method. Now, in this lecture, we will discuss about the time complexity of an algorithm, and then we shall go back to I mean the formal definitions of the three standard complexity notations, asymptotic complexity notations. Okay. So I've shared my screen. I hope all of you can see my screen. Okay. Now, time complexity. So time complexity means the execution time of the program. When we are running the program, how much time is being taken by the compiler or the processor to complete the process of the execution. That is what we mean by time complexity. Now, how to measure the time complexity? Okay, in space complexity, we can still calculate theoretically, both in theoretically and practically, how much size is being allocated or being invested. Okay, memory is being invested to perform to complete the program execution. Similarly, we can also measure as a very, very very easy process to practically calculate time complexity. Just you require a stopwatch. Whenever you start running the program, you start the stopwatch, and whenever the program is finished, you close the stopwatch and measure the time required by the algorithm. That is the easiest way to compute the time, execution time of your algorithm. Now, the thing is, theoretically, how can we justify the time? We have to theoretically measure the time complexity to address many many questions, many challenges. Okay, so we can't always apply trial and error process while analyzing algorithm because we are supposed to be engineers. So engineers pre-plan everything before launching their product, okay, or algorithm. So whenever I am trying to launch my algorithm, okay, so whenever I am going for finalizing the algorithm implementation, before that I have to analyze my method, my logic, okay. So algorithm analysis means program implementation is not yet done. So theory, in the theory classes, we are understanding what are the different type of data structures and also how to analyze the algorithm. Okay, related to those data structures, etc., etc. And in the practical classes, we are implementing in C language these data structures scheme in, or algorithms which are related to data structure and searching, sorting mechanism, etc. Okay, but before going into the laboratory, before going for the code implementation, excuse me for a second. Yeah, sorry. What was I just telling you? Okay, algorithm, right. So, yes, so before going into the laboratory for code implementation, we must have the prerequisite knowledge what we are supposed to do. For example, we are doing next searching or something, a basic searching operation, linear searching and binary searching, which are the fundamental searching mechanisms we will be studying next, right? So linear searching and binary searching. So we should have a clear understanding of the algorithm of the what is the algorithm of linear search, what is the algorithm of binary search, and we should have a prerequisite knowledge, okay, of I mean regarding regarding analyzing the algorithms, linear searching and binary searching. What is the graph of the growth of time complexity function in case of linear searching, and what is the graph of the growth of time complexity function in case of binary searching. So these two information we must have before going to the lab, okay, code implementation. Now if I ask you, now one algorithm, linear search does have its own facility, own advantage, binary searching does have also its own advantage. Now in the laboratory, if I give you a data set, I'm giving you a data set, and I'm asking you, okay, do the searching part. I'm not telling you, okay, which searching algorithm you have to apply, linear or binary. Okay, I'm not telling that, but I'm giving you a data set, and you have to perform the searching operation. It's up to you, whatever method you will apply. That up to you. Okay, whether you will apply linear or binary. So now, if I do not have the prerequisite information before going into the laboratory, what method is better, which method is having its own advantage, I will not be able to distinguish, okay, or I will not be able to decide which algorithm I have to use for my searching operation, linear or binary. Okay, and also if I ask you, I mean, to take a larger data set, you may face a problem, technical problem, or some, I mean, complexity analysis related problem. Those are the things. So whenever you are trying to, yes, we will learn something, we will understand, study all the data structure schemes, understand their policies. Every policy is having, are made based on some assumptions, some considerations, to make advantage of some special cases. So in which cases, which data structure will be applicable, which algorithm will be applicable, that understanding we must have. Okay, and that's, and before the code implementation, what I'm trying to say. Okay. So that's why algorithm analysis is important before code implementation. Okay. So I mean, what I mean to say in a single line, whenever you are going for code implementation, the code implementation has to be pre-planned, not runtime code implementation. It must must be a pre-planned process. Okay. Okay, so now the time complexity. So the time TP taken by a program capital P, for example, any program is denoted by P, and that program, the time taken by that program is suppose TP. So that time is the sum of the compile time and the runtime. Okay, the compilation time does not depend on the problem instance characteristics. So ultimately, time complexity is is effectively measured by the runtime window. Okay, so runtime is hence concerned with the time complexity, which is denoted by small TP. Small TP is the time complexity or the runtime. So it involves runtime involves addition, subtraction, multiplication, division, comparisons, loads, loading means assignments, stores, okay, and so on, etc. Okay, so we may hypothetically propose that in the TP n is the number of elements in the data structure, or not only the number of elements in the data structure. There may be some other variables too. So in short, TP of n is the problem instance, is equal to TA, total time for addition operation, total time for subtraction operation, total time for multiplication operation, total time for division operation. If there is any time division operation in the algorithm, then it will be taken into consideration in the calculation of the total runtime. If there is no division, then TD will be equal to 0. If there is no multiplication, Tm will be equal to 0. Okay, like that. So Ta, Ts, Tm, Td, these are the time for a single addition, for a single subtraction, for a single multiplication, for a single division, respectively, and so on. So, and ADDN is the total number of additions, sub n is the total number of subtractions, and MUL n is that is your total number of multiplications. Similarly, DN is the total number of divisions. So we multiply time for a single addition with the number of total additions, getting the total number of time for the entire additions. So this in the and dot dot dot, there may be other operations too, right? So this is how we can hypothetically propose to calculate the total runtime of an algorithm. Okay, now now see this TPN depends on the system and other programs. Why? Because in my computer, addition time taken by a single addition may be different from your computer. Okay, so it varies from processor to processor. That depends on the processor speed. Okay, clocks per cycle. Okay, number of clocks per cycle. So that depends on the system and other programs also. So so it is not possible to generalize the measurement formula of TPM. So what we can do, but the difference is very small. What we can say, okay. So time required for a single addition, or time, and also what happens, the time required for an addition, single addition, is not same as time required for a single multiplication, because these two are different. Multiplication is a repetitive addition. Okay, it's a collection of additions. But this difference between one single addition, one single multiplication is so small that they are almost same, in the order of nanosecond or picosecond or fermisecond. Okay, for for advanced processors. So what we can assume that they are equivalent. Time required for each of these operations are almost same. So we may hypothetically assume that the time required for a single addition or a subtraction or a multiplication or a division or any other operation will take 1 unit of time. 1 unit of time. Okay. So assuming operators take time which is relatively independent of instance characteristics, number of operations. So if all the TA, TS, TM, TD will be equal to 1, if all those T values are equal to 1, then TPN is nothing but equal to the sum of addition operations, the sum of subtraction operators, the sum of multiplications, the sum of divisions. That means the total time complexity or the runtime is nothing but the summation of all the operations, number of operations. That is what we can propose. That ultimately the number of operations could be the measure of TP, which is the measure of program steps to syntactically or semantically meaningful. Okay. So for example, uh, for example, we now come up to this case. So let's consider the problem Sn. Okay, Sn is again the summation of n number of elements. Okay, but these elements. So this is the same example, one specific example of the previous part, which we have discussed in the space complexity. Okay, so that example was summation of any n number of elements. But here also we are adding up n number of elements, but this n number of elements are having a specific pattern. They are forming an AP, arithmetic progression. So we are supposed to add n number of elements starting from 1, okay, and they are following an AP arithmetic progression where common difference is equal to 2. Okay, first n number of odd terms. So in calculating, while calculating this summation, we may again have two approaches. Algorithm 1 using loop, algorithm 2 without loop. Okay. So here, see, um, the T1 is for the first term. Here first term T1, okay, first term, okay. Here T1 equal to, assumed to be equal to 0, initialized to 0, sum is initialized to 0. Read n is the problem instance, the number of elements to be added in the arithmetic progression. Now for r equal to 1 to n, sum equal to sum plus tr. Initially r was equal to 0. right? R was equal to 0. So some, it will, so T, I mean, okay, let me see. Oh, it should be
Sir,
actually,
T1 should be 1.
T1 should be equal to, my mistake. হ্যাঁ মোস্তফা, এই হ্যাঁ একটু ক্লাসে আছে তাহলে ওই দেড়টার দিকে কল করতে হবে, ঠিক আছে? দুটোর দিকে, ঠিক আছে। এই মিটিং আছে কিন্তু সেই হিসাবে, ঠিক আছে? ওই meeting- হ্যাঁ না, ওই ওই সময়টা ব্রেক টাইম একটু নিচ্ছি, 10 মিনিট, 5 মিনিট, একটু দেখে নেবে গ্রুপটা। Acha, T1 should be equal to 1, sum equal to 0. So then sum equal to sum plus TR. So for first case when R equal to 1, it will be sum plus 1. T1 equal to 1. Sum equal to sum plus 1. So in sum we will store 1. Then we are generating the term TR equal to TR plus 2. So 1 plus 2, that is 3. So next term is getting generated and stored in TR. And in the next iteration, that TR equal to 3 is being added with the sum, existing sum. So you are getting sum equal to 1 plus 3. Okay, like that, and so on. So it is going on up to n number of times. So ultimately, the accumulated result is getting stored in sum, and we are displaying the sum. Now, let's analyze in terms of number of steps or the number of operations. So see, T1, I mean, only we are concentrating the for loop. We are ignoring this line, read end, also this line. Okay, these two lines we are ignoring for the time being. Okay, just concentrate on the for loop. So for r equal to 1 to n. So how many times the for loop will be executed? N number of times. Okay, successful operation, successful the number of executions of the for loop is n, 1 to n, n number of operations. And in each of this iteration of the for loop, okay, we will have two additions, sum plus tr, tr plus 2. So number of additions equal to 2 into number of successful executions of for loop is n. So 2 into n. So number of additions equal to 2n. We are only considering the number of additions. Okay. There are many other operations also, assignment operator. Okay. Here also implementation operator in the for loop, r plus plus, etc. So only we are considering the number of additions, and in this case it is 2n. Now let's look on to the second algorithm without loop. Without loop means we can use the formula for arithmetic sum, progression sum. A equal to 1, that is the first term, 1. Common difference D equal to 2. Okay, sum equal to 0. Read n is the total number of elements to be summed up in this progression. And sum equal to, we are using the formula n by 2, 2a plus n minus 1 into d. And after simplification, this will come into the formula of n square. Okay, it will come to n square. Now let us try to calculate the number of additions in this algorithm. Assuming a equal to 1, b equal to 2. Okay, so what is the meaning of, so in calculating 2a? 2a means a is equal to 1, so 2 into 1. So number of addition, it's like 0. You don't have to add one element with another element. 2 into 1 means 2 itself. So number of addition 0. And n minus 1. N minus 1, it's a single addition. N is getting negatively added with 1 to produce n minus 1. So number of addition will be 1. Then n minus 1 into d. And what is the value of d? That is 2. So if it is 2, so n minus 1 into 2 means n minus 1 plus n minus 1. Okay. Like that. So, okay, it may be 1, it may be 2. It depends. So maximum number of addition will be equal to 2. Then roughly, I mean, though you may be opposing me or you may have an argument with me that it should be 1, not 2, but after just a while, you will understand that this number 1 and 2 will not matter that much, okay, in the overall computation. See, so 2a, because we are doing the rough estimation, not exact. So then n minus 1 into d is computed, 2 is computed. Now these two will be added to each other. So 2a plus n minus 1 into d, and that is a single addition, that is number of addition equal to 1. Okay, so that means up to this, we have computed the third bracket part, square bracket part, right? And this overall square bracket part have to be multiplied with n by 2. Okay, so n by 2 into the square bracket, that is n by 2 times the square bracket. That means we can say that maximum number of additions will be n by 2. Precisely, it may be n by 2 minus 1, but okay, in the order of n by 2. Now, what is the total number of additions we have calculated so far? That is n by 2 plus 1 plus 2 plus 1. So n by 2 plus 4. So here in this case it is 2n, here in this case n by 2 plus 4. Now comparing, which one is more, which one is less? So forcibly, let's see. So let's compute 2n, the difference between the number of additions between algorithm 1 and algorithm 2. See, this is my own derivation, my own design to compare the algorithm 1 and 2. You can't find this in any book. There is no reference. Only reference is the lecture notebook. Okay. So please try to understand, and after the class, you may also refer the lecture notebook for better understanding. So now let's calculate the difference 2n and n by 2 plus 4. So 2n minus n by 2 plus 4. I don't know which one is more and which one is less. So after simplification, it is coming as 3n minus 8 by 2. And let's assume that it is greater than equal to 0. I do not know whether it is greater than equal to 0. Let's assume that it is greater than equal to 0. So assuming this inequality is true, can we have a fruitful value of n? Is it true for any positive values of n? Let's try to find out that. So after simplification, you will come up to a point that n greater than equal to 3. So this is not true for n equal to 1. This is not true for n equal to 2. But this inequality is satisfied for n greater than equal to 3, where n is any positive integer. What does that mean? So number of additions to be performed in case of algorithm 1 is more than number of additions to be performed in the second algorithm. Whenever total number of elements n, those are being added, is greater than equal to 3. So that means time complexity. That means more time will be required in case of algorithm 1 because number of additions is more, and less time will be required in case of algorithm 2 because number of additions is less. Only when n greater than equal to 3. When at least 3 elements are being added. Okay, so that means algorithm 2 is more time efficient compared to algorithm 1. Whenever you are trying to add up at least 3 elements in the arithmetic progression. And this is true for any arithmetic progression. Because we are not bothered about what we are adding. We are bothered about how many we are adding. That is the n. Okay. So in this case, algorithm 2 is better than.
Sir, in the first algorithm, how we are getting the number of additions to n? Sir,
in each of the for loop, we are adding sum plus tr, one addition, and in the second line, we are adding tr plus
okay, sir. Okay, sir. Understood.
Okay. So I hope all of you understood this part. You liked it. Okay. Now coming to asymptotic notations. Again, we are revisiting the previous lecture 4. The function, time complexity function. I hope now you are in a position to understand, okay, what do we mean by time complexity, space complexity, and throughout the course we will be mainly dealing with time complexity, not space complexity. That is not in your syllabus. So now formally, let's say the time complexity function Fn will be termed as Vigo notation of Gn. Only if there exists some positive constants C and Ng such that Fn less than equal to C and Gn, C into Gn for all n greater than equal to Nc. Okay. So this is an analytical part. So whatever, there should be some analytical definition. So as to make our conclusion more foolproof. Okay. So we had this example. If you are having a time complexity function Fn equal to 3n plus 2, and that is your Vigo notation of n, because we can find the positive constants C and N0. Okay, see, 3n plus 2 can be said that it is less than equal to 4n. But is it true always? So let's proceed further if it is true or not. So assuming that 3n plus 2 is less than equal to 4n, we are getting value after simplification. We are getting a value of n which is greater than equal to 2. So this condition is not satisfied for n greater than n equal to 1. n, that's fine. But for n greater than equal to 2, this condition is very satisfied. Okay, so we are getting a positive constant value of n0, that is 2. We are getting a positive constant value of c, that is 4. So then we can say that f is equal to order of n. Okay, this is your y order of n. This is your gn part. This is your gn. This is your fn. So fn is less than equal to c into gn. Okay. Okay. Now coming to a theorem. It's a very popular theorem and very powerful and useful theorem. I normally call it as a polynomial theorem. So if any time complexity function is in the form of a polynomial of degree m, okay, let's say fn equal to am n to the power m plus dot 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 plus a1n plus a0, then fn will be equal to b connotation of n to the power of m, the term corresponding to the highest degree of the polynomial. So order of n to the power m. Okay, and we can prove that the theorem is provable. So let's see the proof. So fn, we can say that okay. So we can say that fn is less than equal to summation over, where this expression we can write as a sum form, using sum operator. The summation over I equal to 0 to n, I equal to 0 to I equal to n, ai ni. Suppose this is your fx. Okay, so any summation fx, polynomial function fx, can be said that this is less than equal to, okay, mod of a1x1 plus mod of a2x2. We can say that it's a primary definition. Okay, so we are given that in our case in the theorem that fn is equal to am n to the power of m plus dot 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 a1 n plus a0. Okay, so that is obviously can be written as less than equal to mod of n. N is a positive constant. N is positive. Here n is greater than 0. 1, 2, 3, 4. That is the number of, that is the problem instance that is positive. So am, but the coefficients of the polynomial may not be positive always. They may be negative. Okay, in this case we had an example 3n plus 2. It may be some 3n minus 2. It may happen that. Okay, so ultimately the coefficients may be negative, but ultimately if the coefficients are negative, we can say that the overall summation polynomial summation is less than or equal to, right? So this is very intuitively very true. If some of the coefficients are negative, then the overall sum will be less than if all the coefficients would have been positive, right? তাই নাকি বুঝতে পারলাম কি বললাম? যদি এই সামেশনটা সবকটা n তো পজিটিভ, তাহলে n এর পাওয়ার যাই থাকবে সবকটা পজিটিভ, সেটা নিয়ে প্রশ্ন নেই। তো সবকটা কোএফিশিয়েন্ট যদি পজিটিভ থাকতো তাহলে মনে করো একটা রেজাল্ট এস পেতে, ঠিক আছে? আর যদি কোনো দু একটা কোএফিশিয়েন্ট, একটাও যদি কোএফিশিয়েন্ট যদি নেগেটিভ হয় তাহলে তো ওভারঅল ভ্যালুটা একটু হলেও কমে যাচ্ছে, তাই না? তাহলে এখানে কোএফিশিয়েন্টগুলো পজিটিভ বা নেগেটিভ আই ডোন্ট নো। সাপোজ পজিটিভ অর নেগেটিভ হোয়াট এভার, সাপোজ দ্যাট ইজ s1, তাহলে s1 should be less than or equal to, so it will be equal to s if all the coefficients are positive, and it will be less than s if at least one coefficient is negative. Okay, so how to represent this s? where all the coefficients are positive. That's why I am applying modulus. So modulus of m to make the coefficient positive forcefully, and n to the power of m, then plus modulus of a, m minus 1, m minus 1, n to the power of m minus 1, then plus dot dot dot, plus dot dot dot, mod of a1 into n, and plus mod of a0. Right? And this expression is equal to, is nothing but the summation over, okay, mod of ai, okay, into n to the power of I, where I is equal to, sorry, where I is equal to 0 to m. That has been written in the PDF. That is, Fn is less than or equal to summation over I equal to 0 to n mod of ai into n to the power of I. That is very intuitive. So now, or now in the next step, you can say that, okay, so you forcefully bring n to the power of m out of the summation operator, and accordingly here it will be n to the power of I divided by n to the power of m. So that's why it is n to the power of I minus n. Okay, so now in the next line, fn less than equal to n to the power of m, which is like a constant. N is a problem instance, some value 10, 20, 30, 40. Okay, uh, what I'm saying, sorry, the n is the problem instance, n is the variable. So it is n is the variable, right? So this is the variable part, n to the power of m. Okay, and this is the summation of the modulus of coefficients. Summation of modulus of the coefficients. So for a specific function, n is changing, not the coefficients. Okay, so the sum of modulus of coefficients is treated as a constant. Okay, this is like a constant. So we can think that this overall summation portion as a c in this formula, fn less than equal to cgn. So that c is the constant part multiplied by a variable part. Okay, so this is like that constant part, summation over mod of ai, and this is your variable part, n to the power of n, which we can think of as gn. So it is in the form of c into gn. So fn less than equal to c into gn. So is it true for all the n? So this is the generalized expression for any function where n greater than 0. So here, what is 0? This is your n0. So n greater than 1 means, n greater than 0 means at least n greater than equal to 1. That means n0 is greater than equal to 1. So we are having a positive constant n0, which is 1, for n greater than equal to 1. This overall inequality, fn less than equal to c into gn, is getting satisfied. And also this c is a positive constant. This c has to be a positive constant, positive constant c and n0. So n0 is found to be 1, and c is found to be the summation of this. Summation of what? All the modulus of coefficients. Modulus are positive, summation of modulus is positive. So overall this summation is a positive quantity. So hence c is a positive quantity. So for there, that means there exists some positive constant c, which is here the summation of mod of ai for I equal to 1, 0 to n, and a particular n0 value which is equal to 1. Here n0 equal to 1, c. The inequality fn less than equal to cgn is satisfied. So any such polynomial function of degree n, fn, will be in the order of n to the power of n, where n is a fixed quantity for that particular algorithm, and hence the theorem is proved. So as this is a less than or equal to based theorem, this is like, it's an upper bound of the function fn. So gn is like an upper bound of the function, time complexity function fn. When fn cannot be more than the right hand side, fn less than equal to cgn. So fn, the left hand side, which is the your time complexity function, that can't be more than the right hand side. So in other words, the right hand side is like setting the upper threshold for the function fn, right? That's why this big O notation is called upper bound of the time complexity function. What is the upper bound? G is the upper. Graphically, what does that mean? Graphically, it means, suppose this is the graph and you have a function growing like this. So this is your G. Some polynomial function of degree n. It may not be a quadratic. Okay, it's a growing function. So it's an exponential, exponentially growing function. Yes, n to the power m. It's an exponential function. Now you may have some fn which is like this, a straight line. A straight line, or some quadratic, like quadratic, or some cubic, whatever. But whatever functional graphs you will have corresponding to fn, those should always lie below gn. That is what means by fn less than equal to c into gn. The functional values of fn should be always less than or equal to the functional values of cgn. It may touch when fn is less equal to cgn, then fn is touching, exactly coinciding with gn, cgn. Gn or cgn. C is just a multiplying factor, constant, it's not a problem. But less than means the function fn is lying below the curve of gn. It can't intersect like this, it can't go above gn in any portion. Okay. So this is the geometrical interpretation of the theorem. The upper, what is meaning by upper bound? It can't go above it. Okay. Gn is like an upper threshold. 27, 3 minutes are left. So the function fn is equal to, another notation is the function fn is equal to big omega of g if there exists positive constant c and m0 such that fn greater than equal to cgn for all n greater than equal to m0. Similar definition of omega notation as we have seen in the big O notation. Only one thing is getting changed here, it is greater than equal. That means we can expect that this omega notation will give us the lower threshold, the lower bound of the term complexity function. Okay. So analytically, we can take up some example to understand this notation. That suppose fn equal to 3n plus 2, and we can say that highly that for any n positive, 3n plus 2 is obviously true that it is greater than equal to 3n. I am adding 2 with 3n, so 3n plus 2 will be more than 3n. That's obvious. Okay. So this is your like c into gn. Here gn is equal to n and c is 3, and this is true for all n positive, means n greater than equal to 1. N can't be equal to 0. N is the number of elements. It can't be 0. So at least one element should be there in the data structure. That's why n greater than equal to 1. That is starting. Okay. So we have satisfied that fn greater than equal to cgn for n greater than equal to 1. So m0 is equal to 1 here, c is equal to 3 here. We can say that 3n plus 2 fn is equal to big omega of n. Similarly, you can try out with other examples, fn quadratic polynomial or an exponential function, time complexity function. And for exercise, you can try to prove the theorem in a similar fashion what we have understood in case of big O notation. So it gives us the lower bound of fn as g. Okay. Now see, in the graph we are having an upper bound. Now we have got a concept of, let's say, lower bound like this. Any function will always lie above this curve gn, and that is the meaning of big omega notation. Okay, that means fn, so this is the overall space, this is the entire space where Fn can lie above Gn. This is your space for big omega notation. And for big big O notation, this is the black curve, this is the upper threshold. So this is the entire region, this is the entire space where Fn can lie. So this is the space for Fn using big O. This is the space for Fn using big omega. So again there is a problem. So the space is very large, infinite space. So what if we can have a finite space? What if we can have a finite space? Okay, suppose we have both upper threshold and both lower threshold within which the function Fn has to confine. Something, it may be a straight line, some polynomial like this. Then it would be better. We are better analyzing, we are visualizing the functional growth far better, right? So from this motivation, there is another notation which is big theta notation. The function Fn is equal to big theta of Gn if and only if there exists positive constant C1 and C2 and N0 such that Fn less than equal to C2 G2. This is very similar to the big O notation, and this portion is very similar to the big theta notation, big omega notation. Fn is greater than equal to C1 G. Now if we combine big O and big omega, we will come up to another notation which is theta. So Fn is lying in the range between two polynomials, two bounds, C1 G1, C1 Gn and C2 Gn. And we must have positive constants C1, C2 existing and also N0 existing, which is positive. So for example, 3n plus 2, another same example. 3n plus 2 greater than equal to 3n. We have just seen the big omega, which is true for n greater than equal to 1. And also 3n plus 2 is less than equal to 4n for all n greater than equal to 2. So for n, now if we combine these two, then these two will be also intersected. So for n greater than equal to 2, we are satisfied that 3n plus 2 is lying in the range 3n to 4n. So this 3n means here this is your going to be C1, this is your going to be C2. Okay. So this condition is satisfied for all n where n greater than equal to 2. So this is your like N0. This is more precise analysis of the function Fn. More precise. We are having both upper bound and lower bound in case of theta notation. You may try the same with other examples, the quadratic and the exponential. And also you can go for the proving of the theorem. Okay, so this notation provides us more precise bounds for Fn as G. Okay, so that's all for today's lecture. I hope all of you have understood well and you are enough motivated. Again, you refer the lecture notebook for your better understanding, and the reference book references and introduction, the fundamentals of computer algorithms by Horvitz Sahani, okay, Raja Sekhar. Thank you for listening. If you have any doubt, you can ask me.